Okay, next, what happens if you have to look for absolute maximum and absolute minimum? All right. So remember your region, the domain. Of course, the domain in this case has to be closed and bounded in order to find to guarantee an absolute maximum or minimum. Typically, your closed and bounded region or domain looks like this. Okay, or maybe a square, or maybe a circle, right? And so f is defined, and you're restricting it on this region R, and of course, it's a real valued function. All right, so here is the sort of a step-by-step procedure. Find all critical points. Why? Well, because typically these absolute maximum and minimum points could happen at critical points, right? So maybe this is a point where it is, the f is the largest. Maybe this is a point where f is the least or the smallest, right? So they could happen internally or at some interior point of R, but that's not always the case, right? Remember in calculus 1, we have to check the boundary points. So that's what you have to do. By the way, do not apply the second derivative test. The second derivative test only tells you what's happening locally. All right. So no second derivative test is necessary. Even if you find let's say you found that this is a local maximum. Okay. That may not be useful because there may be a point over here where f is larger. And so the local argument doesn't do any good. If you do this, trying to apply the second derivative test for absolute maxima and minima, you're basically wasting your time because you don't really need to know if a point is a maximum or minimum internally, locally. All right, and then second, you find all maximum and minimum on the boundary. Now, this is the tricky part. Maybe this is the trickiest part of the section, 7.4. All right, so try to find all the maximum or minimum on the boundary. If it's a curve like this, you may have to parameterize it. If it's a square like this, you may have to restrict your f for for fixed x or y values. You'll see that. I'll try to do a couple of examples here. If it's a circle, then you may have to parameterize that also, right, in terms of t. And then you use the methods in calculus 1 to find the maximum and minimum, right? And then after you have picked all the critical points possibly, all the internal critical points and all the maximum or minimum on these boundary points, in this case, like if it's a square, you have to check for all of these on every one of those four edges, right? And then once you find all the candidates for maximum and minimum points, then you compare the value of f, x, y at all of those points. Now you will have finitely many points, okay? And so the highest of these, okay, so the maximum of those is the absolute maximum, of course, right? And the minimum of the values, f of x, y, that would be the absolute minimum. So, I mean, this is just like what you did in calculus 1, except you don't have just two boundary points anymore, A and B. You have infinitely many boundary points because these are, regions surrounded by either a square or a circle or a rectangle or something. Okay, so let's do an example here. Find and by the way, if you are given a stuff like, a situation like this, there's only one absolute maximum value and there's only one absolute minimum value. Okay, if R is closed and bounded by the extreme value theorem, you are guaranteed to have one absolute maximum and one absolute minimum. You can see why there are no two absolute maximum values, right? And now the point is, you may have an absolute maximum value of, let's say, 100 here, and maybe another point it's 100 here, maybe another point 100. Okay, so there may be 3 points where the absolute maximum occurs, but the absolute maximum as the value is only 1. Okay, all right, so find the absolute maximum and the absolute minimum for this function, x squared minus xy plus y squared. Now, if I say that, you can clearly see there's no absolute maximum or absolute minimum, because I can make x to be like 3,000 and 5 million, and I can make this into a large number. There's absolutely no maximum. It can go forever. All right. It can go down to negative infinity if I can switch x and y, manipulate it. So I have to restrict the domain on the region, the triangular region R, and I will define my triangular region. My triangular region R is this triangle. It's half of the 4 by 4 square. Okay, so this line is y is equal to x. Okay, is that clear? So this is closed and bounded, of course. It's a closed and bounded region. And this is a continuous function. So by the extreme value theorem, there will be an absolute maximum and there will be an absolute minimum. Okay, so the question is, if you restrict this function on this domain R, okay, what's the highest number that f becomes and what's the lowest number f becomes? That's very simple. Right? And the answer, you follow these procedures. All right, so let's go ahead and try. In fact, you may want to try this first. Okay. Now, before you do this, remember, you can find the interior possible local maximum or minimum in the process we did in the first half of this section. Right? But then you have to think of this edge and this edge and this edge. We have to consider them separately and find a possible maximum point on each edge, possible minimum point on each edge. And maybe you'll have to worry about the corners, right? And so you have a lot more work to do than just finding local maximum and minimum and saddle points. Okay, so let's see what happens. You can continue to watch this, or you can sit and try to figure out at least the critical points. Yeah, why don't you find the critical points and come back. All right, let's find the critical points. Fx is 2x minus y. Fy is negative x plus 2y. You want set both of these equal to 0. Okay, system of linear equations in this case. How do you solve that? Here's 1, here's 2. Okay, now there are a bunch of ways you know or you have learned on solving systems of equations. You can do a Gaussian elimination method if you're a big fan of matrices. I guess most of you aren't. You can do Gauss-Jordan elimination method if you're even a bigger fan of matrices. Or you can do things like substitution and elimination, right? If you remember what Kramer's rule is, that's another thing you can use. Anyway, there are a bunch of ways for you to do. I think the simplest way for this one is let's multiply equation 1 by 2. Okay, you see what's going on, right? That's 4x minus 2y is equal to 0. And then you can add these, right? If you add these, you get 3x, and of course, these will cancel. Is equal to 0. Ooh, that's easy. So x has to be 0. Right. Now, it's a system of linear equations. One side is, it's called a homogeneous system because, one side is all 0. And so and by the way, the 2 by 2 matrix corresponding to this, for those of you who are in linear algebra, that 2 by 2, system 2, negative 1, negative 1, 2, this is not singular, it's invertible, so there is a unique solution, and the unique solution can be found by using the inverse of the function. But anyway, you don't need to know all that. If x is 0, then by equation 1 or equation 2, y has to be also equal to 0, right? So what this is saying is 0, 0 is the only critical point of f. In anywhere, okay, not just restricted to R, but anywhere. This is the point. So here's the point. Okay, this is the only critical point. It doesn't really tell us a whole lot. It just means that there's nothing interesting happening in the inside of R. Okay, there's no local maximum or minimum or saddle point inside of R. Now we get to the interesting part. Okay, so allow me to draw this again. All right, so here I am going to call this side 1, side 2, side 3. Okay, so now let's go to the boundary. The boundary consists of 3 edges or 3 sides. S1, okay, what do you know about S1? This, by the way, is 4, 4, right? S1 goes from 0 to 4 along the y-axis. And so one thing you should know is x is equal to 0. Right? I'm going to rewrite the equation so I can have this handy right next to me. This is a function I am considering if x is equal to 0, oh yeah, and then y goes from 0 to 4. Okay, so f on this line segment, remember x is equal to 0. So that just becomes y squared. Okay, and so y squared, all right, let's take the derivative of this with respect to y. That's 2y. Okay, and that's, of course, 0 only at y is equal to 0, right? So as long as far as this point is concerned, or this line is concerned, this is the only critical point. I say critical point in the sense of calculus 1. Okay, if you are considering S1 as my line segment, which is a domain of this restricted function, then the only interesting thing happens, meaning critical point, it happens at this origin, right? We see the origin was something that we have discovered as a candidate anyway, or one of the usual suspects. Okay, so I don't really need to know that this is a special thing that I have to investigate later. Okay, but the point is, there's no other point. There's no other point on this line S1 where an interesting thing is happening, like a possible maximum or minimum. Okay, so that's good to know. All right, S2 is where y is equal to 4 constant, right? And x goes from 0 to 4. Remember, for absolute, to find absolute maximum or minimum, you always have to do this kind of analysis. So that would be a long problem for you. Okay, I'm not assigning 15,000 of these questions. I'm giving you a reasonable amount. So please, make sure you do all your homework after this lesson, and you will spend a lot of time doing section 4 homework, just as a heads up. All right, so f of x, y, on this line, S2 turns out to be x squared minus, remember, y is 4, so this becomes minus 4x plus 4 squared, that's 16. All right, now here the derivative is 2x minus 4, and that actually does have a critical point when x is equal to 2. Okay, so something may be happening right here when x is equal to 2. This is a point I have to worry about. Okay, because if you restrict f on S2, this is a critical point for f restricted to side number 2. All right, so we picked up a point, one of the suspects. Okay, we'll have to take him in and take him or her in and investigate. Maybe we'll have to ask a bunch of questions. All right, and then how about S3? S3 is this line, which is y is equal to x. All right, and of course, x is still between 0 and 4. But on this, you can write this totally as a function of x, because x and y are equal to each other. It's x squared minus x times y, which is x squared, plus y squared, which is also x squared. That's just x squared, right? So what I'm saying is, this thing, if you replace y with x, it just becomes x squared minus x squared plus x squared, which is x squared. Now, the derivative of this is 2x, and that only has a critical point at 0. So back again, this origin, this origin here is the only interesting point. Okay, so what we have found in all of this analysis is this. Besides the corners, which still we have to explore, because the corners could be a point of, absolute maximum or absolute minimum. Besides these points, on the edges, this is the only point, extra point we have to consider. Okay, so here's my final analysis, or the final stage of the analysis for the absolute maximum and absolute minimum. Check the value of f, which is, okay, let's go ahead and write this. It's x squared minus xy plus y squared at, all right, so the three corners. Okay, so 0, 0, and then 0, 4, and 4, 4. These are the corners. And then there's one more point we have to consider. That's 2, 4. Okay, so in other words, here's the triangle. I have to check at this point, this point, this point, and this point. Okay, these are the points that we have discovered could be relevant on the edges. How about the inside? There's nothing inside that we have to check, because the only critical point of this function was 0, 0, which we are already considering. Okay, so far, did you get this? Did you get the idea of finding the usual suspects? In this case, we have 4 suspects. And what we will do is we will explore f at each of these points. Okay, we'll evaluate that. And the highest of those points will be the absolute highest of those numbers will be the absolute maximum, and the lowest will be the absolute minimum. Get that? All right, so at 0, 0, it's simply 0. At 0, 4, that would be 0 minus 0 plus 4 squared, which is 16. At 4, 4, that's 16 minus 16 plus 16, which is 16. How about 2, 4? That would be 4 minus 2 times 4, that's 8, plus 16. And that happens to be 12. Okay, so are we okay so far? And so now we are ready to answer the question. By the way, sometimes just because I'm a visual learner, I actually like to write down the values in the picture, right? So at 0, 0, this is 0. And then we have 16 here and 16 here and 12 here. So what's happening here at 12? Okay, so the picture is, so here's what's happening here. This is the XYZ. You know what? Maybe I should draw a little bigger picture here. Okay, follow along with me. What's happening here? I don't know if I can draw a nice picture. I will certainly try my best, but sometimes these things work out better. Sometimes they don't. What's happening here is back on. All right. So at this point, 0, 0 represents the value of 0. And at what is this point? 0, 4. So it's 1, 2, 3, 4. At this point, the value of the function is actually, it's 16. Okay, and then you have, let's see, the region R is actually like this, right? Okay, this is the region R. Okay, and the graph of this function, remember at this point, 4, 4, the value is 16 also. So this goes up to 16. And what's happening on this line or line segment, what did I call it? S2. Yeah, on S2, what's happening is it's going from 16 and then 12 and 16. Okay, and that's what you're finding. So if you restrict your domain to S2, this does become a point of interest. It's a minimum point. Okay, a local minimum anyway. And then of course this goes back to 0 like this. And then this kind of goes back to 0, probably something like this. All right, so this is what's happening, but this point here does represent a point of interest. It just didn't turn out to be absolute maximum or minimum. Okay, but it was a hidden point where we had to figure out. You know what? I don't want to draw this line here because this is confusing. But on the back side, above here, above this line is this parabola that is happening. And that's why this point was of interest. But again, it didn't have to be, it's not a maximum or minimum. All right, so what's the absolute maximum? The absolute maximum is the value, the highest value, which is 16, occurring at 2 points, 0, 4 and 4, 4. Now, I often ask where the absolute maximum occurs. If I ask you what is the absolute maximum, you would like to say the answer is 16. And if I say where does that happen, then you want to give me the x and y coordinates like 0, 4 and 4, 4. Okay, and what's the absolute minimum? Your answer should be 0. And where does it happen? Happens at 0, 0 and no other place on this domain R. So that's the gist of how you find your maximum and minimum. Now, in this case, the region was simple. It has 3 sides. If you have a rectangular region or a square region, you would have to consider all 4 edges, okay? And so, again, that may take some time, but that's how you would do these problems. Okay, I have one more problem I'd like to show you, but I think it's on the handout. So get the other handout out. The other handout looks like this, the optimization, right? And it has a application problem at the end. So let's go to that in our next segment, okay? And take a break if you have to, and then we'll finish this section well after that one handout.